Welcome to the video on hydrolysis of an ester. If we look at the overview of the reaction, we can see when we hydrolyze an ester, we turn an ester into a carboxylic acid. And in the process, the O part of the ester becomes our weakest base and is our leaving group, and that becomes an alcohol. So you can see in this specific example, hydrolysis of an ester is simply going to break this bond right here. We'll put a carboxylic acid there, and then this opens up to become our alcohol. There's two ways that this reaction can be accomplished. The first is in acid, so that would be an acid-catalyzed hydrolysis of an ester. In that case, you really can only have available H+ and neutral water. You will not see an OH- anywhere in that reaction. Secondly, in base, we can only have available to us the hydroxide ion and neutral water. You won't see a positively charged species in that type of reaction. I hope that kind of helps you distinguish between the two. Looking at the acid-catalyzed hydrolysis of an ester to begin with. The first step, we protonate the oxygen of the carbonyl, giving us this intermediate here, where the oxygen at the top here now is positively charged. Now, because that oxygen is protonated, this carbon here, the carbon of the carbonyl, becomes a lot more electrophilic. So we can have a nucleophile, water shown here, react right at that carbonyl, and then this double bond kicks up and we put 2 electrons back on the oxygen. So if you look at our next intermediate, we see that the water has attached. Because it's neutral here, it's positively charged here. And so we have that water attached. We have the original oxygen of the double bond here, and we still have our ester. So this is the first of our tetrahedral intermediates. The next step is deprotonation of this positively charged alcohol. So the base is going to reach out and take that proton and kick the lone pairs of that bond back up onto the oxygen, giving us our neutral alcohol. Also giving us our second tetrahedral intermediate, which is shown here. And this one is all neutral. In the next step, what we're going to do is reprotonate, because we want this group right here to be the weakest base. The best way that we can do that is to protonate it. So if we have that oxygen reach out, form a bond with the hydrogen, giving us that protonated alcohol here, which then becomes the weakest base. Once we do that reprotonation, you see here that we have our third tetrahedral intermediate. Now in the next step, what we have is collapse of the tetrahedral intermediate. And in class, what we called that was the oxygen kicks down and kicks out the weakest base, which in this case would be the opening of the ring. And so when you look at our next intermediate, now we have the carboxylic acid formed here, and then over at the other end of our molecule, 5 carbons away. So if we look here, this is carbon 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's our alcohol. So this OH is this OH. And then in the very last step is all we need is to do our final deprotonation. So we're going to have the base pull off that proton and put the electrons back onto the oxygen, giving us our carboxylic acid molecule that, because this was a ring, our leaving group is an alcohol, and that's in the same molecule. So this here is the acid-catalyzed hydrolysis of an ester. Now, if you move to base-catalyzed hydrolysis of an ester, this is a little more straightforward. So our nucleophile is good and strong. We have the hydroxide ion. It's ready to react as a nucleophile. We don't need to activate this carbonyl carbon by protonating. We just have this very good nucleophile. These 2 electrons attack the carbonyl carbon, kick up to the oxygen, so that we end up with this tetrahedral intermediate. And in the base catalyzed reaction, it's very simple, because the next step, we have the oxygen just kick back down and kick out the weakest base. And in this case, it's opening of that ring, giving us this species right here with our carboxylic acid at one end of the molecule. And then just like in the previous slide, 5 carbons away, we have our leaving group right here, which is O-. Now because this is a carboxylic acid and the pKa of this species is lower than our alcohol at this end, we can very easily get that intramolecular proton transfer to give us our final product here. Now if we wanted to afford our final carboxylic acid, it would have to be in its protonated form, and so we could, in a second step, at the end of the reaction, we could protonate, or simply put a salt in there so we could stabilize that species. Remember, hydrolysis means to cut with water, and so that's exactly what we're doing. We're taking an ester, we're cutting it with water to give us 2 products. One product is a carboxylic acid, the second product is an alcohol. And in these 2 examples, because we started with a ring, our carboxylic acid and our alcohol were actually in the same molecule. It's important to understand these 2 types of mechanisms, the acid catalyzed and the base catalyzed, as we move forward, and expect to see something similar to one of these 2 on the exam next Thursday.